Dear students, have a nice day. I am Dr. R. S. Ramkumar, Head and Assistant Professor of Department of Mathematics at Sri SRNM College, Satur. So today we are going to see about the countable and uncountable set in the course Set Theory and Metric Spaces. So before going to see the countable and uncountable set, we will see some basic definitions. Our first definition is one-to-one function. So consider a function f from a to b. Here domain is a and codomain is b. Then the function f is called one-to-one or simply 1-1 if f of a1 is equal to f of a2. That means the image of a1 under f is same as the image of a2 under f. That implies a1 is equal to a2. The images are equal, then their pre-images are also equal. So these kind, for any a1 and a2 belongs to a. So these kind of condition occur for the function, then the function is said to be one-to-one. So in other words, for the distinct element a1 and a2, that means a1 not equal to a2 implies their images are also distinct. That is, f of a1 is not equal to f of a2. So thus, if f is 1-1 and b is equal to f of a1, then b is not equal to f of a2 for any a2 belongs to a which is distinct from a1. Thus the function, this one is an example. The function f is defined by f of x is equal to x square, where the domain is minus infinity to plus infinity, is not one-one function. But the function g is defined by g of x is equal to x square, where the domain is 0 to infinity, which is 1-1. Because of, for the function f, 1 and minus 1 have the same images. So f of 1 is equal to 1 square, which is equal to 1, and f of minus 1 is equal to minus 1 the whole square, which is also equal to 1. So for the distinct element 1 and minus 1 have the same images. So therefore f is not 1-1 function. But g is a 1-1 function because of the domain is 0 to infinity. For any element x belongs to 0 to infinity, if you take any two elements, distinct element from 0 to infinity, we get the distinct images. So the one more statement for the one-on function. So a function f is 1-1 if f inverse of b contains precisely one element for each b in the range of f. In this case, f inverse itself is a function. Next one is a equivalent sets. The definition: if f from a to b is a onto function. So here the arrow mark is a symbol like that implies. So that means here the function f is onto and also f is 1-1. So if the function 1-1 and onto, then f is called a 1-1 correspondence between a and b. If there exists a 1-1 correspondence between the sets a and b, then a and b are said to be equivalent. So equivalence need not imply equal. For example, set of all 1, 2, 3 and set of all a, b, c. These two sets are equivalent but not equal because of the entries of the first set is totally different from the entries of the second set. So from this we can deduce the following results. Every set capital A is equivalent to itself. The second one, if A and B are equivalent, then B and A are also equivalent. The first one is the reflexive condition, second one is the symmetric condition, third one is transitive condition. So if A and B are equivalent and B and C are equivalent, then A and C are equal. Okay. So to prove the two sets are equivalent, then first we define a function between these two sets, and then we have to prove that function satisfies the 1-1 condition and onto condition. Next definition is an infinite set. The set A is said to be infinite if for each positive integer n, A contains a subset with precisely n elements. For any n given, we can find out a subset from the given set A. Then the set A is said to be infinite. Okay. Here we use I as a set of all positive integers. So I is equal to set of all 1, 2, 3, etc. Here I is an infinite set. So for any n, we can find out the subset with cardinality n. The set of R of all real numbers is also an infinite set. So these are all the examples for an infinite set. Next we will see about the countable and uncountable sets. First definition. The set A is said to be countable or denumerable if A is equivalent to the set of all positive integers. So we can define a function from A to the set of all positive integers I, and we can prove that f satisfies the condition for 1 1 and the condition for onto. Then the given set A is said to be countable. An uncountable set is an infinite set which is not countable. So for the uncountable set, we cannot define any function with unknown correspondence from the given set, from the given uncountable set to the set of all positive integers. Thus, the set A is countable if there exists a 1 1 function from I on to A. That is, there must be a 1 1 correspondence from I on to I to A. The elements of A are the images f of 1, f of 2, etc. of positive integers. That is, A is equal to set of all f of 1, f of 2, etc. So now the set A is countable. We can label the elements of A. So this one is the first element, this one is the second element. Like that, we can label all the elements of a given set A if A is countable. So this one is an example for the countable set. The set of all integers is countable. So here first we define a function from the set of all positive integers I to the set of all integers. So the elements of the integers are 0, minus 1, plus 1, minus 2, plus 2, etc. Now we define a function. So we have the elements from I are 1, 2, 3, etc. Now the odd numbers from I can be mapped to n minus 1 by 2. That means the odd numbers from the positive integers is mapped to the positive integers in the set of all integers, and the even numbers in the set of all positive integers is mapped into the negative numbers in the set of all integers. So we can define a function as f of n is equal to n minus 1 by 2. For n is equal to 1, 3, 5, etc. So here we consider n as a odd number, and f of n is equal to minus n divided by 2, n is equal to 2, 4, 6, etc. These are all the even numbers. And now this function satisfies the 1 1 correspondence conditions. So from that figure we can easily understand how to map the set of all positive integers to the set of all integers. First we consider the number 1. So this one is an odd number. The map is n minus 1 divided by 2. So 1 minus 1 divided by 2. So answer is 0. So the next odd number is 3. So 3 minus 1 divided by 2. So 2 by 2 is equal to 1. So 3 is mapped into 1. And 5 minus 1 divided by 2. So 4 by 2 is equal to 2. Therefore 5 is mapped to 2. So like that we can map all the odd numbers to the positive numbers. So next, even number, we consider the even numbers. So let n is equal to 2, then the image is minus n by 2. Therefore minus 2 by 2, so minus 1. So 2 is mapped into minus 1, and 4. So minus 4 by 2, so the image of 4 is minus 2. So like that the image of 6 is minus 3. All the odd numbers of the set of all positive integers are mapped to the positive integers, and all the even numbers are mapped to the negative integers. The next theorem is, if A1, A2, etc. are countable sets, then union of an is also countable. In other words, the countable union of countable sets is countable. That means if you consider a1, a2, a3 like that, we have a countable collection of sets, and each set is also countable. So if you consider a1, it contains the countable number of elements. If you consider a2, a3, for any set, you can count the elements of ai. Now we take the union, so union of an, then the resulting set is also countable. So proof is very simple. A1, A2, An are countable, so we can label the elements. A1 is equal to the set of all A1, 1. Here prefix says that the entries in the entries of the position of the entry. So A1, 1 means the first element of the set A1. A2, 1 means the second element of the set A1. So like that, in general, A1n means the first element of the set An. So that Akj is the kth element of the set Aj. Now we define the height, the new parameter Akj to be j plus k. Just add the suffix and prefix. And then A11 is the element of height 2. Likewise, A21, A12 are the only elements of height 3, and so on. So just to add the suffix and prefix, we get the height of the element. Since for any positive integer m is greater than or equal to 2, there are only m minus 1 elements of height m. So now we can arrange the elements of union of an according to their heights. The first height is 2, therefore the first element is a11. The second height is 3, there are 2 elements a12, a21. The next height is 4, there are 4 elements a31, a22, a13. So there are 4 elements. So like that we can arrange all the elements of union of an. So pictorially we can draw. First one is a11, next element is a12, the arrow mark is moving towards a12. So the next one is a21, the arrow mark is moving towards a21. Like that we can draw diagonally, we get all the elements of union of an. So from this we can conclude union of an is also countable, because of all the elements of union of an can be labeled as this one is the first element, this one is the second element. Like that we can arrange all the elements, so we get union of an is countable. Next theorem, the set of all 0, closed interval 0, 1 is uncountable. So that is the set of all x such that x lies between 0 to 1, and consider the end elements 0 and 1 also. Proof, suppose closed interval 0, 1 is countable. So this one is a contradiction proof method. Then the elements of the 0, 1 can be written as x1, x2, etc. Every number in 0, 1 occurs among the xi. So expanding each xi in decimals we have. So x1 is equal to 0.a11, a21, a31, etc. x2 is equal to 0.a12, a22, a32, etc. So like that xn is equal to 0.a11, a2n, a3n, etc. So like that. So here a2n means this one is the second digit of the nth number. So xn is the nth number, a2 is the second digit for the nth number. So let b1 be any integer from 1 to 8 such that b1 is not equal to a11. So now choose an integer b1, so from 1 to 8, and b1 is not equal to a11. So then let b2 be any integer from 1 to 8 such that b2 is not equal to a22. in general, for each n is equal to 1 to n, let bn be any integer from 1 to 8 such that bn not equal to a nn. So diagonally we select all the elements, and other than that element a11 not equal to b1 and a21 22 not equal to b2, like that ann not equal to bn. Now we have a new digits. So from that digits we form a new number y is equal to point b1 b2 etc bn. Then for any n, the decimal expansion for y differs from the decimal expansion for xn. So now we have a new number. We have already listed out all the elements of the closed interval 0, 1 as it is countable. From that all elements, now we form a new element y, so which is a contradiction. Therefore the given set 0, 1 is uncountable. From this we have a corollary: the set of all real numbers is uncountable. Because of 0, 1 is uncountable, R contains 0, closed interval 0, 1, therefore R is also uncountable. Thank you.